Hi, I'm Sheila with Seidel. I'm going to talk about a passive method for forming a 2D reconstruction of a hidden scene using a single edge occluder. The ability to form non-line-of-sight images could be incredibly useful in a variety of applications, including, for example, autonomous vehicle navigation and some search and rescue situations. In this work, we focus on the common scenario where the occluding object is a wall. In this case, light from the hidden side is cast onto the visible floor around the vertical edge, forming a penumbra. By taking photos of this penumbra, we can form reconstructions of the hidden scene. Previous work has shown that the penumbra may be modeled as a linear transformation of the hidden scene, enabling 1D reconstructions, where that one dimension is angle into the hidden scene measured in the plane of the floor. In this work, we form a 2D reconstruction of the hidden scene from a single photograph, as shown in this figure. In estimating range, in addition to angle, we not only add a reconstruction dimension, but ultimately improve our angular estimate as well. In setting up our forward model, we parameterize the hidden scene in cylindrical coordinates. Rho is range into the hidden scene, alpha is the angle measured in the plane of the floor around the corner, and z is the vertical height. The range r and angle theta describe a point on the floor in the camera field of view. Under this parameterization of the hidden scene, and assuming uniform floor albedo, the light outgoing at point P on the floor is the sum of incident light from the visible and hidden sides multiplied by the floor albedo. LH is the sum of all light originating from the hidden scene attenuated by radial falloff. Here we sum across range and incident angle. D is defined to be the distance along the floor between the point on the floor and the scene element. And SH bar is the height adjusted 2D radiosity of the hidden scene. This 2D plan view of the hidden scene is what we seek to recover with our algorithm. In order to further model occlusion in the hidden scene, we assume SH bar is separable in range and angle. Here delta is the Dirac impulse function, SH alpha is the 1D scene radiosity as a function of angle. So for a hidden scene that looks like this, SH alpha would look something like this. Rho H alpha is the scene range as a function of angle. When we plug the separable expression into our equation for LH, we get this expression. So now that we have a continuous forward model, where the light from the hidden side is defined in terms of our unknown 2D hidden scene, using this model we form a discrete forward model. In addition to assuming that SH bar is separable in range and angle, we further assume that the hidden scene is comprised of Q hidden targets. So, for example, in this scene with 2 targets, Q equals 2. SH bar may now be described in terms of Q unknown target ranges, Q target angular extents, and 1D radiosity is a function of angle V. Our objective function has a data fidelity term, a term to promote sparsity in a wavelet basis, and terms to promote positivity of the range and scene, and is solved using an alternating method. Here is one measurement in scene with the corresponding reconstruction. In our reconstruction, we get incredibly high angular resolution with sharp edges between the color boundaries. Note that in the measurement, while you may be able to pick out 2 targets, it's impossible to discern range with the naked eye. In our reconstruction, the 2 targets are detected and placed in range correctly with respect to each other. Here I'm showing a second experiment with 3 hidden targets. In this measurement, while you may be able to pick out a contribution to the measurement from the yellow-blue target and the white cylinder, the contribution from the green-red target is difficult to make out. Range information is even more difficult to pick out in the measurement. Still, in our reconstruction, we detect 3 targets and place them correctly with respect to each other in range. In summary, we've developed a new forward model, proposed an optimization framework for single snapshot recovery of 2D hidden scenes, and edges are everywhere, opening the door for 2D imaging in a variety of applications. For more detail, please see our paper.